My dear students, so we have already started the quantum free electron theory of metals, and in the previous class we had seen the classical theory of conductivity for the metals. Basically the concept that we had taken there is electron is going to behave just like a gas particle, and therefore the kinetic theory of the gases is applicable over there. And from that we have got one relationship. If we apply this concept, 3-4 concept that we had seen, one of the major concept was that electron is behaving just like a gas particle, and therefore the kinetic theory of gas will apply on that. And we had seen that we had taken 3 upon 2 kT is equal to half mv square or vth square, where vth we had called as the thermal velocity of the electron. So if this concept, 4-5 concept that we had seen, that is also called the dude theory, if it is being applied on any metal, then we can get the value of the conductivity, right? So that value of the conductivity we have not derived with the limitation of your syllabus. So that formula I am going to directly take up the value that we are going to derive, and from that in this class we are going to check whether the classical theory is really a solution for the electrical conductivity of metal, or it has some demerits. So here we are calling this lecture as the failure of classical theory of conductivity. So let us see how the classical theory failed, and we require a new theory, and then from the next class we will start taking up slowly the next new theory, which is known as the quantum theory, which came to overcome all those failures. So let us see one by one what was the failures as per the classical theory of conductivity, and then we'll look into the solution once we finish the quantum theory of conductivity. So now let us start the failures of classical theory of conductivity. So first of all, let us see expression for the classical theory of electrical conductivity. So what we are going to consider over there is, let us suppose here we have taken, let me take the marker. Here we have taken any materials, right? And this material has got any cross-sectional area. This derivation is not difficult. It's a very easy. Here we have any cross-sectional area. Let us suppose the cross-sectional area is A, and across this metals we have applied a electrical field. And naturally this metal is made of the atoms, and you have already seen how does those atom behaves, right? That is from those atoms how the electron get free, and they are going to create your electron cloud. So now this is the direction of your this will be the direction of your electric field, right, from positive to negative. So this is the direction of electric field. So naturally the electron is going to flow in this direction inside the metal. So electron is going to flow in this direction. So this will be the direction of the electron. We can call that, let us suppose Vd with the drift velocity of the electron, that is additional velocity which has come due to the electric field, we are calling as the drift velocity. So let us suppose drift velocity is Vd. Naturally in the process it is going to make the collision with the crystals, that is with the lattice, and so therefore if it is going to make the collision, it will take a certain time, average time or the mean time, and that the mean time we are calling as tau. Tau will be the mean time of the collision, and the average length, that is it is traveling before it is going to make the collision, is called the mean free path, and that is called lambda. Maybe about these defining terms you must be knowing, but while before we are going to start the quantum theory, I will introduce you about all these terms briefly, so that you will have the better convenience or the revisions in the solving the numerical problems. So what I'm saying here, these electrons are moving opposite to your applied electrical field. So it will have a certain velocity. That velocity we are calling as Vd. It will take a certain time, right, average time in which it is going to make the collision with the lattice, and that time we are calling as the tau, and it will have a certain mean free path before it is going to make the collision, and that mean free path we have taken as lambda, right? And V is the voltage that we have given to this. So taking up this, we'll be getting the expression for your electrical conductivity. So with this, whatever I have told you, if I am going to make the equations, right, and then if I am going to solve the equation, then I will be getting the expression for electrical conductivity. So applying the dude theory of conductivity, if E is the charge on the electron and N is the number of the electrons per unit volume, then the quantity of the charge crossing the given point in the conductor per unit area per unit time is given by sigma is equal to Ne squared tau upon M. So you must have understood all the terms. Sigma is your conductivity. So conductivity will be given as N, where N is the total number of the electrons per unit volume. E is the charge on the electron. Tau is the mean free time, and M is the mass of the electron. This is your expression for electrical conductivity applying the classical theory, right? So if I'm going to apply this, what I find that is experimentally what I find for the conductivity, that as we are going to increase the temperature, as you can see over here, as I'm going to increase the temperature, the resistivity goes on increasing. So with the temperature, the resistivity goes increasing like this, right? And therefore the conductivity will go on decreasing. So what I'm saying, with the resistivity, as we are increasing the temperature, the resistivity is going to increase, and therefore its conductivity is going to decrease for the metals. Naturally, it is not the case for the semiconductor. So in the case of the semiconductor, the conductivity is directly proportional to your absolute temperature. Here rho I that I have taken here, that is, this is a certain embedded value in the materials. That is, even if you are coming to the absolute zero, its resistivity is not coming to be zero, and therefore its conductivity is not going to be infinite. It will have a certain finite value of the conductivity even at absolute zero. So anyway, this is your classical theory of conductivity. Now let us check whether this theory of conductivity, that is sigma equal to Ne squared tau by N, which we have got this derivation applying the classical theory, particularly it is going to behave just like a gas particle, and you have the electron cloud, you have the electrostatic force between the electron and the lattice. So taking all those concepts, we have derived this expression for the electrical conductivity, and that is given by sigma is equal to Ne squared tau by M. So one by one, let us examine whether this theory is able to, or this theory is capable to explain all the constraints. So let us apply the one by one. So the first condition that we are going to check is the failure to explain the dependence of electrical conductivity on temperature. So we know that as we increase the temperature, the electrical conductivity decreases. So we are going to apply this concept, that this is the experimental concept, on the classical theory of the conductivity that we have derived, and let us see whether the experimental value and the theoretically that we have got from that is able to satisfy or it is not able to satisfy. So what I am saying, electrical conductivity is strongly dependent on the temperature. In metal, electrical conductivity decreases with increasing temperature. So as you are increasing the temperature, so naturally electrical conductivity is going to decrease. Experimentally, electrical conductivity sigma is inversely proportional to temperature. So this is the experimental value that we have observed, that it is inversely proportional to the temperature. So what are we are saying, the experimental value of the conductivity sigma experimental is 1 by is equal to 1 by T, that is inversely proportional to the temperature, absolute temperature, right? Now according to assumptions of the classical theory for free electron, what we have, that electron is going to behave just like a gas particle. So if it is going to behave just like a gas particle, so we should be able to apply the gas law. So what is the gas law? Kinetic theory half mv square is equal to 3 by 2 kT. Since here we are applying for your electron, so here we'll have to call the thermal velocity. So what I'm saying, 1 upon mv th square, where vth is your thermal velocity of the electron, is equal to 3 by 2 kT. Now rearrange this equation and calculate what is the value of the thermal velocity of the electron. So thermal velocity of the electron will equal to how much? 3 kT. Now here naturally 3 is constant, numeric constant, and k is your Boltzmann constant. So what you can say, the thermal velocity of the electron is directly proportional to the square root of the temperature. So more be the value of the thermal velocity, it does mean the temperature is more. Less is the value of the thermal velocity, temperature is less. It's very obvious. There is no problem in this, right? Perfectly we can say that it follows the gas law. But now let us explore it further. Now what we can say, the mean collision time tau is inversely proportional to the thermal velocity. Naturally, why we can say that, what is the mean collision time? That is, the electron is going to make the collision with the lattice. Now it will make the collision with the first, then the second, then the third. So there is a certain average time of the collision between one lattice to second lattice to third lattice. So we have calculated average time taken. Naturally, if the velocity is the more, average time taken will be less, because it will be traveling very fast. So in no time it will travel from one lattice to another lattice, second to third lattice. So naturally it is going to be less. If the velocity is going to be less, then it is going to take more time. So what we can say, mean collision time tau is inversely proportional to the thermal velocity. So what then? So what we can say, the term the mean collision time tau is inversely proportional to the thermal velocity, and the value of the thermal velocity, let us suppose this is equation number A, and here that I have substituted over here. So the tau value will equal to how much? 1 upon square root of t, that I have substituted from equation number 1. Now according to classical theory of conductivity, what we know, sigma is equal to ne squared tau by m, right, where tau is your mean collision time. Now tau value you have already calculated. Let us suppose this is your equation B. So in the equation B you have already calculated what is the value of the tau. So just you substitute the value of the tau. Rest all the things are constant. N is the number of the electrons per unit volume. E is the charge on the electron, right? M is the mass of the electron. So what I can say, sigma will be inversely proportional to 1 upon square root of temperature. So now what we are saying, sigma, that is conductivity, is inversely proportional to square root of the temperature. But what is the experimental value? Sigma is inversely proportional to temperature, not a square root of the temperature, right? So experimental value is, conductivity is inversely proportional to the temperature. But here what we are saying, from this theory that we are calculating, is sigma is inversely proportional to the square root of the temperature. It does mean what? It does not, the classical theory is not able to explain the dependence of the temperature on the conductivity, right? So exactly how the conductivity depends on the temperature, the theoretical value and experimental value are not matching, right? So what we can say, it is not able to satisfy the electrical conductivity dependence on the temperature. Let us see one more. The second is failure to explain the dependency of electrical conductivity on concentration of the electrons. Naturally, the classical theory, what we are saying, sigma is equal to ne squared tau by m. Now where n is the number of the electrons. So if you have the more number of the electrons, the conductivity will be more. So if the number of the electrons per unit volume is more, then conductivity will be more according to your classical theory. Let us apply this and let us see whether we are able to solve this, or still this is also going to be a failure. So according to classical theory, what we have, sigma is equal to ne squared tau by m, where the n is the number of the electrons per unit volume, right? Now in a different type of the materials, we have the different number of the electrons per unit volume. So let us see some table, and then let's compare. So now what we can say, where n is the electron concentration, and therefore what we can say, sigma is directly proportional to the n. So more be the number of the electrons per unit volume, more will be the conductivity. Comparative table shows the comparison of your comparison of the concentration of the electron with their conductivity. Now you see this table. Now in case of the copper, the valence electron is 1, right? This is your last orbit configuration, and number of the electrons per meter cube is 8.45 into 10 power 28, right? This is your copper. Now you see the silver. In case of the silver also, you have the only one valence electron, but what is the total number of the electrons per meter cube? 5.85 into 10 power 28. Now you compare these two conductivity. You must be knowing that silver is better conductor than your copper. Okay, what we are getting over here, 6.3 into 10 power 7, right, which is really more than your copper, 5.96 into 10 power 7, no problem. So here what we can say, the electrical theory of conductivity is going to satisfy on the number of the electrons. So naturally, in case of the silver, we have the more number of the electrons, right? And then sorry, no. Now here you compare the number of the electrons per meter cube. In case of the copper, you have 8.45 into 10 power 28, and in case of the silver, you have 5.85 into 10 power 28. So where you have got the more number of the electrons? Here you have got, in case of the copper, you have got more number of the electrons per meter cube. But in case of the silver, you have got 5.85 less number of the electrons per meter cube. We know the experimentally the silver is better conductor than the copper. But according to the classical theory, that is not happening. What is happening? Here we are getting silver has the more conductivity than your copper. This is your experimental value. This is your experimental value. The silver, the conductivity of your silver is more than that of the your copper. But what we are finding, the number of the electron, just reverse. Let's see some more case. Now let us see in case of the zinc. The value of your valence electron is 2 and number of the electrons is 13.2 into 10 power 28. So huge number of the electrons we have, 13.2 into 10 power 28, right? Now you compare this again with the silver. What is the value of the silver? 5.85 into 10 power 28. Now naturally, if I am going to apply this classical theory, zinc must be far better conductor than your silver and copper. But that is not the case. The conductivity of the zinc is very less compared to your silver and your copper. It is only 1.09 into 10 to the power 7 ohm meter. Now you see the case of the aluminium. In case of the aluminium, you have the 3 valence electron, and then you see huge number of the electrons per meter cube, 18.1 into 10 power 28. But now you compare the conductivity, 3.78 into 10 power 6, and in case of silver, 5.6 into 10 power 7, right? So what we are finding, that this theory is not consistent, right? That is on the number of the electrons, the theory is not consistent. It is not consistently able to say that the conductivity is directly proportional to the number of the electrons per meter cube, right? So naturally this fails. So what we can say, the copper, silver and gold are monovalent atoms. As you have seen, you have the only one number of the electrons, valence electron. Monovalent metals and electron concentration is much lesser than the divalent and trivalent like your zinc, cadmium and aluminium. But the conductivity of the monovalent metals are much higher than the divalent and trivalent metals that we know experimentally. This is in contradiction to the outcome of Dewey theory. So what I can say, the conductivity is not directly proportional to the number of the electrons theoretically, but practically the conductivity is not directly proportional to the number of the electrons practically, but with the Dewey theory or the classical theory, what we are saying, it is directly proportional. So this is another failure. Let's look at once more. Now this is your specific heat. Now you must be knowing that the gas molecules will have their specific heat. So molar specific heat of a gas constant gas at the constant volume Cv is given by 3/2 RT. You must be knowing R is called the Rydberg constant and T is the temperature. So it is directly proportional to your temperature because R is your Rydberg constant. So what we are saying, molar specific heat of the gas is directly proportional to your temperature and R into 3/2. All right. However, as per the classical free electron theory, free electron in metals are expected to behave just as gas molecule, because as we know, this is the classical theory that the electron is free and they are just moving like your gas particle. So naturally this gas particle should also have the molar specific heat. Thus the above equation hold good equally well for the electrons also. Naturally it should hold. So whatever I have got this, CV is equal to 3 by 2 RT, it should be applicable for the electron also, because it is also behaving like a gas particle. But what is the reality? But experimentally, it was found that the contribution of the specific heat of metal by its conduction electron was just CV is equal to 10 power minus 4 RT. Now there you see it is equal to your 3 by 2 RT, that is 1.5 RT, and here it is your 10 power minus 4 RT, which is far lower than the expected value. So expected value should be nearly somewhere 1.5 RT, but here we are getting 10 power minus 4 RT, which is very less in case of any gas molecule. Also, according to theory, the specific heat is independent of the temperature. The specific heat should be independent of the temperature, whereas experimentally specific heat is proportional to temperature. So overall, what we are saying, that this theory also failed to explain this. Therefore, what we can say differently, some point has been missed in the electrical theory of the conductivity while it was being analyzed by Diode, right? So the classical theory have got some problem which is required to be resolved. It does not mean the classical theory is totally wrong. Naturally, maybe one or two point has been missed, which required to be incorporated there, right? Which has been successfully incorporated with help of the quantum theory of conductivity. So from the next class, we are going to look into the quantum theory of the conductivity. So some principle first we have to understand, and then finally that theory will be applying on this conductivity, and then again we'll be analyzing that. So those things will be starting from the next class. Thank you very much for your patience. Thank you very much.